Hello, everyone. My name is Jiachen Li, and I'm an assistant professor in the ECE and the computer science department at the University of California, Riverside. So generally speaking, our research is centered around the intersection of robotics, embodied AI, and control with applications to real-world autonomous and cyber-physical systems. And today I would like to share some insights on embodied intelligence, especially about the trustworthiness aspects, like from individuals to teams. So in recent decades, robots are stepping into both industry and people's daily lives. For example, we can see autonomous vehicles are running on the road, and some companies have robot taxi service. And mobile robots are working in restaurants, libraries, and even people's homes to assist humans in various ways. So the existence of robots makes people's lives more convenient, but also makes the world more complicated with human-robot interaction and robot-robot interaction. However, are the current robots reliable enough? Actually, the short answer is no. We can see a lot of unexpected and unsafe events still happen. In a highly complex intersection without traffic control, human drivers can efficiently coordinate with other traffic participants. And in a crowded scenario full of pedestrians, people can still naturally behave collaboratively, avoid collisions, and comply with social norms. So modern intelligent robots, such as service robots or autonomous vehicles, often interact with humans in such crowded scenarios. And they not only need to reach their destination as fast as possible, but also need to avoid collisions with moving pedestrians and comply with social norms. So to ensure a harmonious coexistence of humans and robots, we must build trustworthy, interactive, and human-centered embodied agents. However, there are several challenges along the way. So let's consider these two autonomous navigation tasks. In the first scenario, the autonomous vehicle wants to make a left turn at an uncontrolled intersection. And in the second scenario, a service robot wants to move around human crowds to reach its destination. So in these scenarios, we can see like the robots need to safely and efficiently coordinate with the surrounding interactive agents. However, human behaviors are highly complex and dynamic, which results from unobservable social interactions. Therefore, an important prerequisite for reliable robot navigation is to actually understand how humans interact with each other and how these interactions will influence their future behaviors. And as a further step, the robots should also learn to interact with humans in a safe and socially compliant manner. So this requires effective interaction modeling methods. And of course, we also need to consider the safety because that is one of the most important aspects in like human-robot interaction, especially in very complex scenarios. And also, if you can see like for certain situations, actually there could be a lot of uncertainty in the behaviors of the intelligent agents, either like human drivers or pedestrians, or even like surrounding autonomous vehicles or intelligent agents. So in such a case, we must have a principled way to identify and model the uncertainty and effectively incorporate the uncertainty estimate into the downstream decision-making framework. Also, robots need to navigate in diverse environments. So what if the robots encounter a situation that they have never seen before? Are they still able to handle it well? So to ensure that robots can deal with diverse situations, the approaches need to be generalizable and robust, especially when we are dealing with out of distribution or long tail cases. Okay, so Um, Now, let's revisit such scenarios. So far, we have been talking about a single agent navigating in these highly challenging scenarios. So what if we have another or even more intelligent agents? They are actually collaborating or they are just coordinating in the same scenario. So in this case, we must also consider how to enable effective multi-agent coordination and cooperation. So in this talk, actually, I want to focus on this novel, like interactive decision-making framework. And then we can start with the single agent case. And after that, I will also discuss like how to extend this single agent framework into a multi-agent framework. So this framework consists of like two major modules here I want to highlight. The first one is the prediction model, which actually takes in the historical observations and generate future trajectory prediction or other types of prediction. And another module is the RL agents, which actually makes the decisions for the intelligent agents. And all of these like challenges actually applies to this like into the single agent situation. So let's first look at this prediction model. And in this model, actually, I want to emphasize the challenges of interactions and generalization. So in our context, we care about the relations or the interaction patterns between interactive agents that regulate their behaviors. For example, in these scenarios, we can see leader-follower relations when the agents share similar paths, and collision avoidance relations when the agents have potential conflicts, group relations when they move in similar patterns, or even some other relations that may not be easy to define. And humans can naturally identify these typical relations, but it is challenging for robots. And this is where our relational reasoning methods come into play. So in our framework, we use graphs to represent multi-agent interacting systems. And in this intersection scenario, there are several interactive vehicles. And we treat each vehicle as a node in the graph and their relations as the edges. And then our proposal is that we want to enable dynamic relational reasoning, which is to infer the underlying dynamic relations in an unsupervised manner. So as I mentioned earlier, the interactions between agents regulate their behaviors. So we propose to infer the agent relations from their observed behaviors. And at the same time, effective identification of the underlying relations can in return improve the behavior modeling and prediction. So our proposal is to infer relations from and for behavior prediction. So basically, we define a multivariate dynamic system where X is the state of all the agents and C is some context information. And the goal is to learn a prediction model F to generate future trajectories based on the historical observations. And we infer the relations as an intermediate step of the prediction. And our prediction framework consists of two major components, a graph structure learning module for relational reasoning, and a graph-based predictor that adopts the learned graph for future prediction. So for a certain scenario, we define two types of nodes, the agent node and the context node. And then we construct a fully connected observation graph and perform message passing to aggregate the node information on the edges so that the edge attributes encode the relational information between a pair of nodes. And we propose that the edges have different types to represent different relation types. And our key insight is to infer the relation types through the edge type classification. And by sampling the type from the inferred distribution for each edge, we can generate an interaction graph that will be used by the graph-based predictor. And this procedure actually corresponds to the graph structure learning module in our prediction framework. And in the graph-based predictor, each edge type has a distinct edge function for message passing. So this ensures that the final prediction highly depends on the inferred interaction graph structure. Meanwhile, as the scenario evolves, the relations between agents may change over time. So another key insight is to evolve the interaction graph adaptively with a recurrent neural network for long-term prediction. Okay, so now let's look at these two scenarios where the blue car is at different locations. Although it may have the same types of relations with the surrounding vehicles in both scenarios, the level of interaction strength may be different. So here I use the thickness of the lines between agents to indicate the interaction strength. And similarly, pedestrians may also pay different levels of attention to their neighbors. And based on these observations, in follow-up work, one of our contributions is to estimate the interaction strengths for better aggregated interactions. And the interaction estimation module is integrated into the graph-based predictor. Okay, so for now, so far we have been talking about pairwise relations, but we also observe that humans often move in groups, such as friends or family. And when robots navigate in human-involved environments, they should respect human space and avoid intruding into human groups. So to achieve this goal, the robots need to understand which pedestrians are in the same group and how they will behave as a group in the future. So this actually motivates us to reason about group-wise relations. And our key insight is to infer multi-scale hyperedges to model the intragroup and intergroup interactions. And the hyperedge can connect more than two nodes without constraints, which can naturally represent group relations. And we designed a learning method to infer a probabilistic incidence matrix where each number in the matrix represents the probability that a certain agent is connected by a certain hyperedge or in a certain group. And then we can sample a hypergraph based on the incidence matrix to represent the inferred groups. And because definitely groups can have different types, we further infer hyperedge types to construct the interaction hypergraph. And different colors in the interaction hypergraph represent different group types. So here we show the predicted trajectories in the first row and the inferred relations in the second row. In the second row, different colors of arrows represent different types of relations. We can see that the same type of relations shares similar patterns. Although we don't predefine the meanings of the relations, the model can capture some meaningful relations without supervision. For example, the cyan arrows indicate car following relations, and the dark blue arrows indicate collision avoidance relations. And based on the learned relations, the model predicts future trajectories very close to the ground truth in the first row. Similarly, we can see interesting relation patterns between pedestrians. For example, the cyan arrows capture leader-follower relations, and the dark blue ones capture the collision avoidance relations. So far, all the results are obtained on the same dataset used for training. What if the robot encounters entirely new scenarios or unseen scenarios in a different dataset? So we evaluated our method on new datasets without further training, and we can see that the learned relations can generalize well to new scenarios with similar interaction patterns. And our method also achieves the best generalization performance in trajectory prediction. And by comparing the predicted future trajectories, we can see that the model with group relations better captures the group behavior patterns. So for example, in the first case, the model without group relations predicts trajectories with collisions between group members. Well, after considering groups, the trajectories show better coordination within the group. Also, in the second case, the model without the group relations predicts divergent trajectories of group members, while after considering groups, the model can predict consistent group behaviors. So the key takeaway here is that pairwise relational reasoning, as well as group-wise relational reasoning, identifies explainable and generalizable interactions and improves the prediction accuracy. Okay, so this is about the prediction model in our single agent decision-making framework. Now let's look at the RL agent part, which actually generates behaviors or the actions of the robots. So let's look at the task or the environment for the social navigation. Actually, there are quite a few major principles for social navigation, such as safety, comfort, social norms, agent understanding, as well as some other relevant principles. So in this work, we actually consider decision-making under the prediction uncertainty. So in the previous work I have mentioned, we only consider the most likely behaviors of the surrounding agents, but we actually didn't quite understand or estimate the prediction uncertainty. So in this work, actually, we quantify the prediction uncertainty, which can subsequently informs and guides the behavior of the agent. Yeah, and this is our an overview diagram of our decision-making framework that considers the prediction uncertainty. So first, we have an adaptive conformal inference module to identify or to quantify the prediction uncertainty. And then we incorporate this uncertainty estimate into a constrained reinforcement learning framework. And actually, we specifically incorporate the uncertainty into the cost function or the constraints of the constrained reinforcement learning framework so that our decision-making, the actions or the decision-making process is uncertainty bounded or risk bounded. And in this case, the learned RL agents will actually consider how the uncertainty, how is the uncertainty in the surrounding environment, then how to handle this uncertainty, especially to avoid highly uncertain areas. So let me show some visualizations of our test cases. The first one is in-distribution evaluation, where our method enables safer and better decision-making under uncertainty. And we also did a lot of different out-of-distribution evaluation. For example, we can have rushing humans where the speed of the humans are much higher than the training environment. We also changed the pedestrian model into a different one so that it can generate different behavior patterns. And the last one is the group environment, where multiple agents or multiple pedestrians naturally form a group, and also the group will evolve over time. And we show that our method shows robustness to velocity variations, policy changes, as well as group dynamics. And this table also shows the quantitative results in the out-of-distribution scenarios. And we particularly show that the success rate and the collision rate are much better than the state-of-the-art baselines as well as some ablation settings, especially regarding this generalization performance. And we deployed our models or policies trained in the simulation on a real robot. And actually the robot can actually behave very safely and then effectively interact with the surrounding pedestrians. And at the same time, they can reach their destination efficiently. So the key takeaway here is that constrained reinforcement learning with conformal uncertainty quantification enables generalizable safety in out-of-distribution scenarios for social robot navigation. Okay, so far we have been talking about the single agent scenario, but how to actually extend this framework into a multi-agent framework where we can actually consider multi-agent coordination and cooperation. So basically, in the new or in the multi-agent framework, we will have multiple robots, where each of them also have the prediction model as well as the RL-based decision maker. And instead of behaving as an individual agent, they actually need to cooperate in both the prediction process as well as the decision-making process. So let's first look at how they can do cooperative prediction. So let's take the connected and automated vehicles as an illustrative example. So this is the canonical single agent framework where we have the perception module as well as the prediction module to generate the future trajectories. But in the multi-agent framework, we propose to actually have collaborations and information sharing in both the perception part as well as the prediction part. So this is the high-level overview of our prediction, cooperative perception and prediction framework, where we actually have like you can see, we extract the bird eye view features individually first, but they have an information sharing as well as information fusion mechanism to actually share the bird eye view features between different agents. And then each agent will generate their individual prediction of the future environment. However, we also found that an additional prediction aggregation is necessary because even with the cooperation in the perception phase, like the different agents, they may make different predictions. And the reliability of their predictions may be at different levels. So in this case, it will be beneficial if we actually consider how these agents can leverage the best of each world, and then they can share their predictions, and the agents may adopt or incorporate others' predictions in their own prediction so that each of them can make a good prediction of the complete environment. So here we show some illustrative examples. So basically, we can see that the multi-agent cooperation enhances perception and prediction by reducing the occlusions and improving the accuracy through the prediction aggregation. And also, we show some demonstration videos where we compare the future predictions between without cooperation and with cooperation. Yeah, and this also shows some quantitative results. Basically, we can see that our approach with cooperative perception and prediction reduces the average prediction error by a large margin. And also, we actually found that this approach better handles some out-of-distribution scenarios. Okay, so this is about the cooperative prediction. And after we have a good cooperative prediction, we also consider how to do cooperative prediction, how to do cooperative planning under uncertainty. and in the multi-agent situation. So actually the key insight is that to enhance robustness, we estimate the pixel-wise uncertainty of occupancy prediction from each robot and share it with others. And then we design an uncertainty-aware prediction fusion module that allows the ego robot to take predictions with lower uncertainty, which is effective when an individual robot makes an incorrect prediction or a prediction with a high uncertainty. And then we incorporate this like uncertainty-aware occupancy prediction into the cost function of the constrained multi-agent reinforcement learning algorithm. So the reason why we use occupancy prediction here rather than or instead of the trajectory prediction is that especially in indoor scenarios, there could be a lot of static obstacles with different shapes. And in this case, like a trajectory representation is not sufficient anymore. We do need like a more flexible representation of the environment, such as the occupancy representation, to represent both static and dynamic obstacles. And actually, so here we show some illustrative test examples. The key challenge in this scenario occurs when a pedestrian emerges from behind a wall corner and crosses the right ego robot's path. And in the non-cooperative baseline, the robot fails to anticipate the pedestrian's motion due to occlusion, reacting only after full visibility, and finally collides with the human. But in contrast, our approach leverages shared observations from nearby robots, enabling the ego robot to perceive occluded regions and predict the human behind the wall. And this improved awareness allows the robot to detect potential risks earlier and proactively adjust its speed and direction, and eventually successfully avoid the pedestrian. And in another scenario, actually this constrained space with like a highly intense crowds poses challenges to the prediction model. And with uncertainty quantification, our framework allows the red ego robot to avoid intruding into the high uncertainty areas and adjust its like a direction and speed in advance. And eventually, we can see the right robot is able to escape from the cross. And here we show an illustrative example in the real world. Basically, like the moving robot here, it wants to reach the destination, which is indicated by the blue star. And actually, before it can observe the moving human, it already starts the detour in advance. So that benefits from that there is another robot that is sharing the real-time information with this moving robot that about the human, like the pedestrian. In this case, like the moving robot actually can incorporate the prediction of the pedestrian into its own decision making, even though locally it cannot actually observe the pedestrian. Yeah, and we also found that like our approach can achieve much better performance in out of distribution scenario because of the cooperative uncertainty quantification. So the key takeaway here is that the multi-agent cooperation enhances perception, prediction, and planning through efficient communication and cooperative uncertainty quantification. Okay, so so far I have talked about the cooperative prediction and cooperative planning under uncertainty, mostly in the navigation tasks. But what if the tasks are more complex, which requires semantic reasoning, task allocation, and planning? So especially like when we have heterogeneous multi-robot systems who are doing collaborative tasks. So actually in this case, we first can consider that maybe we can use large language models because they have strong reasoning capabilities for task allocation and planning. But the downside is that they are sometimes not reliable because of hallucinations. They may generate some plans that are not feasible at all, maybe physically feasible, or there could be some safety issues. And we can also consider classical planner, right? Because they are highly reliable and even verifiable. But the issue here is that they typically don't have any semantic reasoning capabilities. So in this work, we actually propose propose to integrate or unify the best of both worlds of the large language models for the semantic reasoning part, as well as the classical PDDL planner. So the key insight here is that instead of using large language models to generate plans directly, we generate the PDDL representations, like the domain descriptions or domain representations, as well as the problem formulations that the PDDL planner can directly takes into account. So the first thing I want to show is like a complex task, which is to microwave a plate containing an egg and tomato. And our framework can identify the target objects and then generate a feasible plan for multiple robots where they are cooperating with each other. And another more interesting case is a wake task. So the instruction here is throw away any trash and prepare for the shower. So actually, it will be difficult to identify what is trash and how actually the robot should prepare for the shower. But because of the strong reasoning capabilities of large language models, our framework can identify what are the trash, in the current scenario. And also, the model also identifies that to prepare for the shower, then actually it needs to maybe turn on the lights, open the shower, and prepare the towel for the users, right? So this illustrates that unifying the strong semantic reasoning capabilities as well as the reliable task planning capabilities from the classical planner would actually generate the best performance. So now we have an effective centralized task planner. But what if the robots are decentralized and need to explore individually in a totally unknown environment? So this is the last work I want to quickly discuss today. So we formulate a multi-agent, multitask embodied question answering framework where multiple agents needs to answer a list of questions or a group of questions from the human users, where they need to actually coordinate efficiently and then also intelligently identify what areas they should navigate or explore to actually obtain the answers to those questions as soon as possible. And we actually propose an efficient multi-agent communication framework where actually the key insight is that not all the information are relevant to each agent, right? So when you are designing a communication framework, when you try to send the information or the messages to the other teammates, you want to make sure that everything you send is is true, or everything you send is fact. There shouldn't be any hallucinations, or also it shouldn't involve a lot of redundant information that could be actually distractions for your teammate. So the key insight in this work is that we leverage conformal prediction to generate a calibrated set of options with confidence guarantees. And only the options with conformity scores above a certain threshold are useful. So in this case, our framework actually filters out all the hallucinations, and all the informations that could be redundant or could become a distraction for their teammates. And then we also design this downstream efficient exploration module that takes in the messages from other agents and do a local aggregation of the information. And eventually they will decide how to explore the environment effectively. So lastly, I want to show a video of some real world demos. And actually, this video should involve some audio. If you cannot hear anything, please do let me know. Yeah, because the audio directly explain what is happening in this real world scenario.
The first scenario takes place in an office. At the beginning of exploration, Robot 2 sees a monitor, but isn't confident enough to answer Robot 1's question, so it initiates communication. Meanwhile, before receiving the message from Robot 2, Robot 1 spots a white plate relevant to Robot 2's target object, bread, and shares this information. As a result, each robot navigates to the location shared by the other and successfully answers its assigned question. Finally, Robot 2 continues exploring and answers its remaining question. The second scenario takes place in a multi-room environment, with the main scene set in a cafe. At the beginning, each robot explores the large environment to locate its assigned target objects. Robot 1 is the first to find a target object, a blue backpack, and successfully answers one of its questions. While continuing its search, Robot 1 clearly sees a TV, which is relevant to one of Robot 2's questions, and helps Robot 2 answer it. Shortly after, Robot 1 spots a monitor, but isn't confident enough to answer Robot 2's related question, so it communicates this to Robot 2. Subsequently, Robot 2 navigates to the location shared by Robot 1 and successfully answers the question. Meanwhile, Robot 1 answers its final question and concludes its exploration. Finally, Robot 2 moves into another room and successfully answers its remaining question. Together, these two demos highlight the effectiveness and deployability of our method in real-world environments.
Okay, so basically the key takeaway of this work is that uncertainty quantification with conformal prediction enhances the reliability and the efficiency of communication through confidence-aware information calibration. Okay, so this is a quick summary of all the key points I covered in my talk. And finally, I would like to thank all of my brilliant students as well as collaborators and sponsors. I'm happy to take any questions.
Yes, we have a lot of questions. So thank you. First of all, thank you so much for this illustrative example about embodied agents. So the first question that we have is, it's more like a comment that we saw in the chat. So participants shared that the agents were lagging or choosing the wrong direction due decision uncertainty, and it was extremely hard to debug without logs. So I want to, because I saw that message and okay, what debugging or observability practices do you suggest for identifying root causes in complex agent systems as the ones that you showed today?
Oh, okay. Yeah, that would be a great question. So basically, in our case, like we particularly focus on the multi-agent interactions, like how to identify the interaction patterns, right? So, and another thing is about like the safety part. How do you actually enable like either like both physically safe and semantically safe agents? So, I think mainly like the key insights I would like to share is that like to actually design some explainable intermediate representations here. For example, in the relational reasoning part, so basically like although our final goal is to generate the future predictions, but we want to see whether the model actually captures the relations or the interaction patterns, and whether those patterns are somehow interpretable or explainable. And by looking at these latent representations, like the latent interaction graphs, we can actually check whether the interactions the model captures are reasonable. And at the same time, because we suppose that, or we basically assume that these interaction patterns should have real influence on their actual generated behaviors, right? So when we actually manipulate some of the interactions, we want to see whether the resulting behavior actually reflect the change of the interaction patterns. So basically, through these intermediate representations, it will help us to debug the whole system and to see whether the model actually captures some useful patterns that we expect. Yeah, and another thing about safety is uncertainty is a very useful indicator about how challenging the current situation is, and especially how confident the model is about the current scenario. And when the robot encounters some out of distribution or unseen situations, that can be typically reflected in the quantified uncertainty, maybe like a higher uncertainty estimate. In this case, it can inform the downstream decision-making part. Also, currently, I'm not very confident. Then you need to maybe take a more conservative strategy when you are doing the crowd navigation or interactive navigation. So those are I would say, the major insights or observations from my existing works. Yeah.
So there is another question that is, so can the agents determine or score how much success they had in completing their assigned task?
Oh, that's also a very good question. So in our current work, in the works I already presented in this talk. Basically, the evaluation is typically done by the environment or the benchmark itself. Actually, the agent doesn't directly evaluate themselves. But in future work, I believe we can actually we can try to enable some self-evolving agents. And in this case, actually, in this case, the agents should be able to, for example, imagine that the agent is trying to achieve a long horizon task. For example, like a long horizon manipulation. For example, make a cup of coffee. And in this case, the robot needs to first find a cup, right? And then put the cup to the coffee machine. And after that, push the button and then eventually take out the cup. And in this case, actually, there are multiple steps, and the agent should identify or figure out whether the last previous subtask is achieved or not, right? So we are trying to actually enable the robots to anticipate potential failures, identify potential risks, and do some kind of evaluation by themselves so that they can decide how to proceed further. So I think this would be a great direction for future work.